Hello students, the purpose of this video is to get you acquainted with rate of change. Hopefully you've watched our video on linear versus exponential models, and when we talked about linear models we said that these measure constant rate of changes, and so we know we'll be looking at linear functions. We love linear functions because again they are constant, so it allows us to be able to find a pattern and then easily make predictions about what we believe will happen in the future. So if I look at this particular model, this visual representation, you see that I have a graph. You'll notice that I have given you the equation 3t plus 1. And we know that this is in the form of mx plus b. So m is representing my rate of change. It's letting me know how steep my line is. And when I talk about steepness, I could be positive going up or I could be negative falling. And so my rate of change in this case is 3. And then I have a y-intercept of 1. This is my y-intercept value. And that just means the point that crosses my y-axis. So when I am at 0, my corresponding y value is at 1. So you can kind of think about your starting value is 1. Okay, so we can see that since our slope or our rate of change is 3, that's equivalent to 3 over 1. So every time I go up 3 points and over 1, I should appear on my line. So let's see if that's the case. So I'm going to go up 1, 2, 3, and over 1. And up 1, 2, 3, and over 1. And so you see my green dots do in fact appear on the linear function. Now my second model I have here is a quadratic, and so I just wanted you to see how bringing in a quadratic term can drastically change your function, because thinking about rate of change is completely different here. You're no longer moving in a consistent rate. And when we look at quadratic functions, they actually make what we call a parabola. And so you have this part of the parabola that's falling, and then you have this part of the parabola that's increasing. So depending on what part of the function you're concentrated on, your corresponding xy values are doing different things. So I wanted to give you an example where we could look at rate of change. I highly encourage you to pause this video and try to work through these problems. And I'm actually working with you through these problems as well once I provide you all with the solutions. So the table below gives the population of California since 1970. So we have year 1970, year 1980, year 1990, year 2000, year 2010. And we want to find the average rate of change for each decade. So you're being asked to find it for each decade, which means it wants you to find the values from 1970 to 1980. It wants you to find the values from 1980 to 1990, the value from 1990 to 2000, and then the values of 2000 to 2010. So there's going to be 4 separate equations that you're going to have to make. For the sake of making this video not too long, I am going to do the 1970 to 1980 year for you. So we are finding the average rate of change from 1970 to 1980. All right, so you can think of your years as your x values, and you can think about your population as your y values. And so going from year to year, we're going to see what's the difference in our x's, and then what is the difference in my y's as well. So remember that average rate of change is equal to m, which is your slope. And we actually have a slope formula. Our slope formula is the difference between our y values over the difference between our x values. So y2 minus y1 over x2 minus x1. When we're looking at these values, we're basically considering 2 different coordinate points. So if I look at my chart here and I am calling my years as my x's and I'm calling my populations as my y's, I can make various different coordinate points. So I have the point 1970, and it corresponds to 20. Keep in mind this is in millions, but for the sake of the example, we'll just use the whole number value. And then we have 1980, which corresponds to 23.7. And so it doesn't matter how we label these. The key to remember is that once you label one value, so if I choose to label this x sub 1, its corresponding value must be the same sub value. So it would have to be y sub 1. If I wanted to call it 1970 x sub 2, then I could call the value 20 y sub 2. So x1, y1, and then x2, y2. So you notice the sub value is just trying to differentiate between my different points. And now I'm going to plug these into the average rate of change formula. So I have 23.7 minus 20. Those are my y values over the difference in my x values. So 1980 minus 1970. And I'm going to go to my handy dandy calculator. And I'm going to type in 23.7 minus 20. And that gets me a solution of 3.7. And then I'm going to type in 1980 minus 1970, and that's going to give me a solution of 10. And if I do 3.7 and divide that by 10, that reduces down to a final answer of 0.37. So I have found that my average rate of change, or my slope, whichever word you'd like to utilize, is 0.37. Looking at letter B, during which decade was the average rate of change the largest, you are going to need to calculate each individual year. So remember we said we need to find the average rate of change between each year, and you're going to look for the largest value among those 4 years. Now, looking at letter C, use the average rate of change during the decade in 1990 to 2000 to approximate the California population in 1993. We have a similar problem in letter D, so I'm going to go ahead and work out C and let you do D on your own. So in order to solve this, I need to know what my average rate of change is from 1990 to 2000. So I'm going to find that first. So I have 1990 corresponds with 29.8, and I have 2000 corresponds to 33.9. I'm going to call this x1, y1, x2, y2. So I'm going to locate my slope first, 33.9 minus 29.8, all divided by 2000 minus 1990. And then I'm going to use my handy dandy calculator, and I'm going to do 33.9 minus 29.8, and that gets me 4.1. I'm going to do 2000 minus 1990, and that's going to give me 10. And I'm going to do 4.1 divided by 10, and that's going to give me 0.41. So this is just the average rate of change part, but the question wants me to approximate the population in 1993. So if I know what my population was in 1990, so if 1990 had 29.8, and again, this is in millions, but we're just going to refer to it as 29.8 for now. And I know that my slope is 0.41, then I am just going to add 0.41 to get my value in 1991. So I'm going to take my 29.8, and I know I increased by 0.41, so I'm adding 0.41, and in 1991 I can predict I had 30.21 million people. And then to get to 1992, I am going to again add my rate of change because this is a positive value, so I'm going to add 0.41, and that gets me 30.62. And one last time, because I want 1993, I'm going to add 0.41 again, And when I add my 0.41, that gets me 31.03 million individuals estimated for 1993. I would do the same process in letter D, but I do want to make a note. So you're being asked to find the average rate of change from 2000 and 2010, but you're being asked to approximate the population in 2009. And so we added up. If you notice, when we found our slope between 1990 and 2000, we started at 1990, and then we added 3 times to get to our year 1993. Well, it would probably make more sense in letter D to start with 2010's population and subtract whatever slope value you find to get a year below it. Now, you're welcome to start at 2000 and add 9 different times to get up to your year 2010, but again, that would be much more work rather than you just starting at 2010 and subtracting your slope once to get to the year 2009. So moving on to our second example, again, a very similar example. We have a different application. So the table below gives velocity of a skydiver in seconds during their free fall. So you have your time in seconds. This is going to represent your x values, and then you have your velocity, and that would represent your y values. So again, each of these top and bottom values can be placed together to represent coordinate points. So if I'm going to find the average rate of change of velocity for each 10-second interval, that means I want to find the average rate of change from 0 to 10, from 10 to 20, from 20 to 30, from 30 to 40, from 40 to 50, from 50 to 60. So you're going to have to find each of those separately. So like before, I'll go ahead and do one of those intervals for you. I will do the 0 to 10. So I have 2 coordinate points, 0, 0, and then I have the point 10, 129. And I'm going to label my respective points, x1, y1, x2, y2. I have 129 minus 0 all over 10 minus 0, which reduces down to 129 divided by 10. And if I use my calculator and do 129 divided by 10, I know I need to move my decimal place 1 over, and I get 12.9. So I know that the average rate of change in this interval was 12.9. And again, you would need to continue this process to find all of your other interval average rate of change. And in letter B, you're going to compare all the average rate of changes that you got for each interval. You're going to see which was the largest, and that would be your answer to letter B. Now in letter C, use the average rate of change from 10 seconds to 20 seconds to approximate the skydiver's velocity 19 seconds into free fall. So I need to find the average rate of change from 10 to 20 seconds. So at 10, I was moving at 129. At 20, I was moving at 153. I'm going to figure out my average rate of change. And when I solve these particular values in the numerator, I have 153 minus 129. That gets me 24. 20 minus 10 gets me 10. And when I solve and simplify, I get the solution 2.4. So that lets me know that I am increasing at a rate of 2.4. So this problem, I was measuring from 10 to 20 seconds, but it's asking me about 19 seconds. So if I just start at 20 seconds, so at 20 seconds, I know that I was at 153. If I wanted to get from 19 to 20, that means I needed to add 2.4 to get to the value 20. So I'm going backwards because I'm starting at 20 trying to get to 19. So in this case, I'm going to subtract 2.4. And when I do 153 and I subtract 2.4, that brings me down to my 19-second interval, which is 150.6. Okay. Alrighty, I hope that you found this video helpful. Please, I encourage you to do the other intervals for practice on your own, as I didn't go through them. But I hope you found this video helpful. As always, if you have extra questions or concerns, please don't hesitate to reach out to me, and I wish you all a wonderful rest of your day.